So in the last video, we identified parts of an atom and the structure of an atom. In this video, we are going to specifically focus on one particular part of the atom, and that is the electron and the electron cloud. So our topic for today is examining the emission spectrum, and we'll explain what that means due to various electrons in an atom. And you should be able to describe the behavior of electrons in the emission spectra of various types of atoms. Our essential question is, how does the emission of light help us identify the identity of an atom? So again, please spend just 3 minutes at the end of this video writing a 1 to 2 sentence summary answering this essential question. So starting off, let's do a quick review of the electron cloud. Again, remember, in the electron cloud, this is where our electrons are located in the atom. Okay, our electrons are not located inside the nucleus. They're only allowed in the electron cloud, which is kind of the outskirts of the atom. Okay, and last video, I briefly went over this concept, but within the electron cloud, electrons are limited to the space that they can take up. And there are a limited number of electrons that are allowed in each space. So these spaces that we are talking about are what we refer to as energy levels. So I'll write that down. So again, the first space that electrons are going to be able to take up is the first energy level. And our variable for energy level is a lowercase n. Believe it or not, only 2 electrons are allowed in the first energy level of any atom. The next space that electrons will fill up in the electron cloud is energy level number 2. So again, with this energy level can actually accommodate 8 electrons. Our third energy level can accommodate even more electrons. Fourth energy level can accommodate even more than the third, and so on. So as these electrons get further away from the nucleus of the atom, they're going to be increasing in energy level. Now, what I will say about this is a really cool pattern, and if you've never studied the periodic table super closely, you will haven't probably been able to appreciate the genius that went into designing the periodic table yet, but these are really cool patterns that appear on the periodic table, and one of those is the electron energy levels. So you will notice that the periodic table has rows and columns, and they're not all complete. And there is a reason behind that. And as I spoke about in the last video, as you go down in the number of rows on the periodic table, that is indicating the increasing number of energy levels that those atoms have. So in our first row, a hydrogen atom has its atomic number 1. It has 1 proton and it has 1 electron typically. And it is in the first energy level. So indicating that hydrogen and helium atoms, helium has 2 electrons, they're only really going to have 1 energy level. Those electrons are they have multiple energy levels, but those electrons are primarily going to remain on that first energy level. So we label that n equals 1 for indicating that those electrons are only going to be on the first energy level. Now, if we go down a row, that's indicating that we are on the second energy level. So, for example, neon has its first 2 electrons in the first energy level, as you can kind of see in this picture here. To your left, and it also has 8 more electrons in the second energy level. So this atom that I've actually drawn right here is a neon atom. Okay, so it's got its nucleus, it's got 2 electrons in the first energy level, and it has 8 electrons in the second energy level. So you can see that by counting the boxes on the second row, which is our second energy level in the periodic table. And neon, you will see, has a total of 10. That's its atomic number. So 2 in the first energy level plus 8 in the second energy level equals a total of 10 electrons. Okay, so that is kind of a brief overview of how those energy levels work. Again, with the genius of the periodic table, we can also determine generally how many electrons each atom is going to have using its atomic number. Now remember, that's the number in the top right-hand corner of every box on the periodic table, and that indicates the number of protons of that particular atom. Now, if that atom is neutrally charged, meaning it has no positive or negative charge, because what can happen is, well, I'll back up. If that atom is neutrally charged, it means that the number of protons in the atom are equal to the number of electrons. So what we can assume is the atomic number is also representing the number of electrons in that atom, assuming it's neutrally charged, meaning it has not gained or lost any electrons. It doesn't have an excess or too few electrons. If it lost electrons, it would develop a positive charge because it's losing some negative charge. If it were to gain electrons, it would be developing a negative charge, meaning that it would be have an excess of negative charge. So again, our atomic number is representing the number of protons as well as the number of electrons in an atom. So that allows us to, using those energy levels, determine where those electrons are going to generally be in that electron cloud. So a really unique thing happens with these electrons in these various energy levels of an atom. So keep in mind, we are referring to them as energy levels for a reason, because it's going to indicate the amount of energy in that atom. So these electrons are actually not restricted to remain on a particular energy level. They can move around to different energy levels within the atom. It's just that they tend to prefer a particular energy level. And that is what we call the ground state. When an atom is in its ground state, those electrons are going to be in all of the energy levels that they prefer. So they are all going to be located in their lowest energy levels possible. So, for example, a hydrogen atom in its ground state is going to have its singular electron in the first energy level. It does not like to increase its energy level. So that is a grounded atom there. Now, what can happen is if one of these electrons moves up an energy level here, and you can kind of see that, say we had one electron move up in an energy level from energy level number 1 to energy level number 2. Then that atom would enter an excited state, meaning that electron, it has one or more electrons in a higher energy level than its ground state. So this is giving that atom a little bit more energy, which is why we refer to that atom now being in its excited state. So when it's in an excited state, it has a more potential energy, basically, is a good way of thinking about it. Now, again, since these electrons are able to move, let's say an atom started in its excited state, and then that electron decided to move back down to its ground state. Now, it just went from a position of higher potential energy to a position of lower energy. So it decreased its energy level. It went from energy level number 2 to energy level number 1. As a result of that, it's going to release some energy. It's decrease the amount of energy it has, so it has to release some of that energy. Now, when it releases that energy, it's going to be released in the form of a photon. So you might be familiar with the word photon before, but basically what a photon is a particle or a bundle of light. And this is kind of getting into what we call the photoelectric effect, which describes, if you recall from our video about light, that light can behave both as a particle and a wave. So a photon is describing the way that light behaves as a particle. So we've talked about light as a wave before. A photon is a release of light in the form of a particle or, a bundle of particles as a result of an atom going from its excited state to its ground state. Now, what happens here is sometimes this photon is in the form of visible light. So we can actually see it, which is super, super cool. And remember from our video on light, the colors that we see are dependent on the frequency and the energy of that light wave. Again, I know that we just talked about light as a particle, but remember, light is also going to behave as a wave. So we start to see if an electron is moved from a very, very high energy state all the way down to its ground state, it's going to release a photon that is higher energy. So we actually start to see kind of a purple color when it is being released from a really, really high energy level to a really, really low energy level. So that is going to determine the color that we see in that photon. Same thing happens if, say, it was just not quite as high as an energy level as it would be if it was releasing purple light. You would see blue light all the way down to the lowest energy level possible to be an excited state would result in the release and visual of red light. So again, the energy level that electron is coming from in its excited state is going to determine the colors that we see. Now these colors that we see as a result of these electrons returning from their excited state to their ground state is what we call the emission spectrum. And every atom is going to have a unique emission spectrum because every atom, as we talked about up here, has a unique number of electrons. So these emission spectrums, or emission spectra, the plural, allow us to determine the type of atoms that we are working with. So there's a really cool instrument called a spectrometer, which analyzes emission spectra of various elements. So it can determine what element is in a particular substance by examining the emission spectra of that substance. So say we have an unknown substance, we can use a spectrometer to visualize the emission spectrum of that substance. And then we can match it up with the known emission spectrums of these various elements or the atoms to determine what that substance is made out of. So these are just a couple examples of something you might see in a spectrometer. So say we had a substance that is filled with hydrogen atoms, you would see some purple light, some blue light, some green light, and some red light. And again, that's the top row is our hydrogen. Our second row, you would see helium. Say we were looking at a substance full of helium atoms, you'd see quite a bit more colors. You'd see a little bit more green, a little bit more yellow. Same with our third row is the atom sodium. So if a substance was made out of sodium atoms, we'd actually only see really blue and yellow here. And our last row that I pulled up an example for is mercury. So if we were to find a substance full of mercury, this is kind of what mercury's emission spectrum looks like and what we could expect to see when we use the spectrometer on that substance. So it's a really, really cool phenomenon that kind of combines this dual nature of light, being a particle and a wave, and our knowledge of light, as well as our knowledge of the structure of an atom and an electron's behavior. So I hope this video was interesting and it gave you a pretty good overview of how electrons behave and how that results in an emission spectrum for a particular atom. Again, please don't forget your summary at the end of your notes, and I look forward to discussing this with you more in class.